welcome back, everybody. We are going to talk about the last statistic in our section of looking at relationships in data. So this one is called the linear regression. It is the final inferential stat that you have to learn. So let's go ahead and jump into it. So what we're going to cover in this section is the basics of linear regression. We're going to talk about how the regression equation works and something called the regression line. And then our final video will look at regression in the context of hypothesis testing. So let's get into the basics of linear regression and talk about what it is and how it works. So linear regression is the next level of correlation. Think of linear regression as correlation's big sister. Okay? Correlation examines the relationship between two continuous variables. Linear regression also examines the relationship between two continuous variables. But here's the difference. Here's where it builds on correlation. Linear regression is specifically looking at how well one variable, x, predicts the other variable, y. So it's not just looking simply at are they related, but it's really looking at how well x predicts y. So linear regression is looking at the degree to which one variable is dependent on another predicting variable. It's very similar to the independent-dependent variable relationship that we looked at with t-test and ANOVA. It's looking at how one variable is affected by a predicting variable. Okay? Now, linear regression is useful because it can kind of assess causality with variables that cannot be manipulated through experimentation. Now, linear regression is not purely experimental, so it's not truly examining causality like t-test and ANOVA can, but it's kind of the next best thing, especially when you're in situations where you can't directly test causality. Let me give you a very common example here. So when it comes to looking at the relationship between smoking and lung cancer, we can't experimentally test for this relationship, because to do that, you would have to take humans, or usually some kind of animal that we test in our place, and we would have to split them up into different groups and have some smoke a certain amount of for a certain amount of time, and then have some not smoke at all, and then see if there's differences in the cancer rates that you find among the different groups. But that's wildly unethical for us to do with humans and for us to do with even animals, to subject them to that kind of harm. So what we can do is we can take current rates of smoking that we have documented, and we can take current rates of cancer, and we can see, does smoking predict the lung cancer rates? So in a way, we are kind of getting at causality. It seems to make more sense that smoking would cause lung cancer rather than lung cancer causing smoking. So it's not true causality that we're getting at, but it's the next best thing. So let's talk about what it is and when do we use it. So a linear regression assesses the predictive relationship between two variables. It looks at the predictor variable and it predicts a dependent variable. So does the PV predict a DV? So when would you use it? You would use it when you want to see if two continuous variables have a predictive relationship, where the X or the PV predicts the Y, the DV. So how this works is that, let me say it this way. Linear regression is primarily concerned with prediction. Now, prediction is a technical term. It is the computation of future outcomes based on knowledge of present factors. We're trying to predict what would we find based on what we currently have. Now, the prediction computation is based on the correlation of the two variables. This is why linear regression is the next level of correlation, because it uses correlation in the calculation of its prediction. Now, the connection here is that the stronger the correlation between the two variables, the more accurate the prediction tends to be. So weakly related variables tend to have very weak predictive relationships. Now let's walk through the logic of how linear regression is calculated. This is going to be very essential for you to understanding how the whole process works. So let's take this question to kind of guide our thinking. Does high school GPA predict first-year college GPA? Okay. So what we know from regression is that a stronger correlation between high school GPA and first-year college GPA would lead to a more accurate prediction between high school GPA and first year college GPA. So the closer we see that those two things are related, the more accurately we can take high school GPA and predict first year college GPA. So here's some data that I have here that we can use to look through this. So we have 10 students here, and we have their high school GPA in the X column, and then we have their first year college GPA in the Y column, okay? So their GPA was calculated at the end of their first year of college, and then of course that's their GPA when they graduated high school on the left there. So I went ahead and plotted on a scatter plot. Take a second and look at the makeup of this scatter plot. You can see that the dots are moderately close together. You can see they're moving in an upward fashion. So maybe there is some kind of relationship there, and that's going to be a precursor to the predictive relationship between them. So so with this data in mind, let's keep going. So we asked the question, what if high school GPA perfectly predicts first year college GPA? What does it look like when X perfectly predicts Y? Well, that's what linear regression is really wanting to do. What it does is it calculates the predicted Y value. Okay, it's a symbol called Y hat. It literally just looks like it has a hat on top of it, so they call it Y hat. The intention was not to be creative, it was to be straight to the point, so Y hat. So what is the predicted value of Y given a value of X? So we have X and Y data already. Using that data, what would Y have been if X perfectly predicts Y? Okay, that's what we're really looking at with a linear regression. So the way that you calculate this is using an equation here, which is Y hat equals BX plus A. It is very similar to an equation you may recall learning from high school algebra, which is Y equals MX plus B. You used that in algebra when you were plotting graphs and doing those kinds of calculations. It's a very similar equation here. The thing is that with Y equals MX plus B, you're actually calculating real Y scores, whereas Y hat is you're calculating predicted Y values based on X values. So Y hat is the predicted Y value. X, of course, is the value of X. A is the Y-intercept. It's the value of Y when X equals 0. So it's like what you get in the equation when you plug in 0 for X. It's also the point at which the line crosses the Y-axis. You'll see that when we go back to the scatter plot. And B is the slope of the line. That's indicating how steep or flat is it, right? What is the angle of the line? You can think of it that way. So let's work through calculating our regression and predicted Y scores here. So at the bottom, I've got the necessary components you need to do the calculations. So go ahead and calculate covariance and then continue on so we can work on the rest of it. So the covariance you should have gotten is 0.299. That is your covariance here. So with the covariance, you can then find the slope. Put the slope on top, and then you can take the variance of X and you put it in the equation there. So what you should get is 0.695. That is your slope. I want you to pay attention here to something very important that's worth pointing out. If you notice, the equation for B is very, very similar to the equation for R. The top part is the covariance. The bottom part is kind of like the standardization. With R, it was the standard deviation of X and the standard deviation of Y. In the slope, it's only X. It's the variance of X, not the standard deviation. But the part I want you to focus on is that it only includes the X variable. The reason for that is because we're trying to predict Y. So we're not basing this equation on Y and X. We're only basing it on X. So that's why the slope only includes X in the bottom part. So the slope is 0.695. You would interpret the slope very similarly to a correlation coefficient. The sign of the number tells you the direction. So if the slope is positive, it means there's a positive relationship. If the slope is negative, it's a negative relationship. The closer the slope is to 0, the weaker the relationship. The further from 0 the slope is, the stronger the relationship. So you interpret B very similarly to a correlation coefficient. Now, lastly, we plug in the numbers that we have here, and then we can solve for the Y-intercept. And the number at which Y is, the predicted Y value when X equals 0, is 0.647. So we can then fill out our regression equation at the top here, and we get y hat equals 0.695 times x plus 0.647. Now, when you have that equation calculated, what you do is then you plug in every value of x, and then you calculate your predicted y value. Let's focus on a few of them here out of the ones that are calculated on the table. Let's look at Joe. So Joe has a high school GPA of 2.50. His first year college GPA was actually 2.20. But if high school GPA perfectly predicts first year college GPA, Joe's predicted college GPA should have been 2.38, which is slightly higher than the GPA he actually got. For Flo, you see that her predicted GPA is a lot higher than the one she actually got. Now for Jerry, his is slightly lower than the one that he actually got. And you can make the comparisons for the other 7 students as well. So we calculate these predicted values because we want to compare them to the actual y values. So if I go back to the scatter plot here, remember, if x perfectly predicts y, it means that x is perfectly related to y. And if x is perfectly related to y, then all the values will line up perfectly in a straight line. So what you can see here is this regression line, as it's called, or trend line, has all of the predicted y values on it, one after the other in a perfect line. Now, the red dots are the data points for the high school GPA and actual college GPA. And they are spread out. And what I want you to pay attention to is that for each person, you can see there's a gap between their actual college GPA and their predicted college GPA, okay? So take Joe, for example. Joe is around 2.20. His predicted should have been 2.38. So you see there's a little bit of a gap there. For Jerry, his is very close, 1.97 and 2. And then for Flo, we can find Flo. It is at 4 all the way at the end there. And hers is at, I'm looking at the wrong one, sorry, 3.8. There it is. 3.8 is her actual one. And her first year college GPA is 2.7. There it is, 2.7, and the gap is from 3.29. That's a larger gap between her predicted and her accurate, or her actual. So what do we do when we compare all these differences? Some are closer than others, some are further than others. What does this mean overall? Okay. Well, the regression line, also called the line of best fit, visually shows us the predicted values of y, as I already mentioned. Now, when you're comparing the y values to the predicted y values, the difference between them is the error in prediction. It's showing you how much error that you have. And if x and y are perfectly correlated, there would be no error, right? If that's actually what happened in real life. Okay. So what do we do with all these errors in the prediction that we can calculate? All the differences between the actual values and the predicted values. Well, the closer the data points are to the regression line, the smaller the errors, right? The closer the actual college GPAs are to their predicted GPAs, the more accurately college GPA is predicting first year college GPA. So what we can do is we can calculate on average how much error do we have. This is called the standard error of the estimate. Okay? It's essentially taking the average of all the prediction errors. Now, the closer this number is to 0, the more accurately x predicts y. Another way we can measure accuracy of prediction is using the coefficient of determination. The number we use to determine the strength of correlation coefficient can also determine the accuracy of a prediction. So let's do that here with our data. So what we see is that we have a standard error of the estimate, which is 0.597, and we have a coefficient of determination of 0.393. Okay. So we can see here that the standard, there's a lot of error in our prediction here. In fact, the error is greater than the accuracy. When that happens, you get a weaker prediction. In fact, the less error you have and the higher the R squared, the more accurate the prediction overall. Okay. Now, You can just use the R score to determine this, but you do need to know what the standard error of the estimate is. But R squared is the traditional number we use to determine how accurate the predictor variable predicts the dependent variable. Now, another way that we determine the prediction is by looking at the slope of the line, looking at B. B is really referring to the degree that the PV predicts the DV. So the closer B is to 0, the lesser the prediction. The further from 0, the greater the prediction, like I mentioned before. So we see that B is 0.695. It's further from 0, which means that the relationship, the prediction is stronger, but it might not be that accurate based on the R score that we saw previously. Okay? So this is essentially how the linear regression works. It is trying to determine how accurate X predicts Y by looking at what Y would be if X perfectly predicted it. And then you compare the actual Y to the predicted Y. The greater the difference between them, the less accurate the prediction is. And so with that, our next video will focus on regression in the context of hypothesis testing.